My name's William. Let's do some math. This video is going to look at another polynomial, and we're going to factor it in order to find all of the zeros or roots. But in this instance, there are going to be complex zeros. So here's our function. F of x is 3x to the fourth plus 5x cubed plus 25x squared plus 45x minus 18. The first step in our four-step process is to identify the max number of roots that the polynomial could have. Because the highest degree is 4, that tells us there are going to be at most 4 roots. The second question you should ask is whether or not they're going to be positive or negative. And in order to figure that out, you need to use Descartes' rule of signs and look at both the function f of x and f of negative x. Looking at the original polynomial, trying to count the sign changes, we start with a positive term, the second term is also positive, the third term is positive, the fourth term is positive, and we only have one sign change here at the very end. So there are at most one positive root. F of negative x will be a polynomial where all of the odd terms have changed signs, and then we will look at the sign changes from term to term there. But again, note that the cube and the first power are the only terms that change signs when you plug in a negative x for all of the x's and then simplify the polynomial. In this case, you're starting with a positive, then we go to a negative, so there's one sign change. Then we go to a positive, there's a second sign change. We go to a negative, which is a third sign change, and then the last one doesn't change. That tells us we're going to have at most 3 negative roots. But because we know that complex roots and irrational roots could come in pairs, this means we may only have one negative root and we'll have 2 complex roots, roots that involve I or that require the quadratic formula to find them. And that's what we're going to have here. So let's get to finding them. We need to first list all of the possibilities. That would be using the rational zeros theorem. To use the rational zeros theorem, you look at the constant term and the leading coefficient, and you build fractions out of those factors. So the 18 there, the constant term, has factors of 1 and 18, 2 and 9, and also 3 and 6. And I'll put those factors from the constant term over factors from the leading coefficient. 3 factors into just 1 and 3. Any of these could be positive or negative, so it gives me a pretty big list here. I could have 1, 2, 3, 6, 9, 18. I could have 1/3, 2/3. 6 over 3 is a 2, which I've already counted. 9 over 3 is a 3, which I've already counted. 18 over 3 is a 6, which I've already counted. But still, that's 8 possible numbers over here, and all of them could be positive or negative, so that's 16 things I have to go through if I want to actually identify the roots. There are a couple of ways to do that. Let's go through the process of plugging in the possibilities. Again, the function was 3x to the fourth, 5x to the third, 25x squared, 45x minus 18. So I will start by trying positive 1. If you just plug that in, you get 3 times 1 to the fourth plus 5 times 1 to the third plus 25 times 1 squared plus 45 times 1 minus 18. Adding all of these positive things up and then subtracting 18 is not going to be 0, and since it isn't 0, that's what tells me 1 is not going to be my root. You can go through and plug in all of these other numbers until you find one. Remember, there is going to be one positive root, so that leaves 7 other possibilities that I can look at in order to find the next root. There is another way, using synthetic division, to see if one of those possibilities is actually a root. Let's try this with a positive 2, and we will do synthetic division. If the end result of synthetic division is a 0, then the number that we put in the box is going to be a root. I'm pretty sure a positive 2 is not the number I'm looking for, but we'll give this a chance just so that you can see the process here. Synthetic division requires you to drop down the first number, so I have a 3 here. Then I take 2 times 3, which is 6. I put it here. I add down, making it 11. Multiply those two together, put it here. That's 22. I add down, which will be 47. Yes, multiply by 2. That's going to be 94. Put it here. Add down. I can already tell I'm not going to end up with a 0. 2 times 139 is 278. Add 18, and I have 260, which is definitely not 0. You can use either of these processes. If synthetic division had resulted in a 0, then we would already have the coefficients for our reduced polynomial. So if you're really comfortable with synthetic division, this is a good way of doing it. But maybe if you have a calculator where you can just plug in the numbers quickly, especially if it's a graphing calculator and you can just plug in the formula, it may be faster to just plug in the possibilities and see if you get out a 0. Well, the positive 1 and positive 2 didn't work. I happen to have some inside information on this one, and I'm going to recommend that we try 1/3. Drop down the 3, multiply it by a third, that's a 1. 5 plus 1 is 6. Multiply it by a third, that's 2. Add those together, that's 27. Multiply that by a third, you have 9. 45 plus 9 is going to be 54. Cut that in a third, and should be 18. When you add those two together, you get a 0. So this is my root, a positive 1/3. Here then we have a reduced polynomial. Remember that we started with x to the 4th up here, so these numbers that came out of synthetic division are the coefficients for my reduced polynomial, which will have x to the 3rd. So I have 3x to the 3rd plus 6x squared plus 27x plus 54. And I could go through again and use the rational zeros theorem, find factors of 54, put them over factors of 3, come up with another number, or I could go back to the list of possibilities that I created up here and go through those and trying to find another root, because I'm looking for at least one negative root. But I do happen to have in my toolbox of algebra skills some factoring by grouping skills, so we're going to try that instead. From these first two terms, I can pull out a 3x squared. I'll be left with an x plus 2. And from these third and fourth terms over here, I can pull out a 27, which is going to leave me with x plus 2. They have an x plus 2 in common, which is great. I'm going to factor that out. And then I have 3x squared plus 27. So these are the two factors in addition to the x minus 1/3 that will get me back to my original polynomial. The reason that I am factoring this way is that this here is an irreducible quadratic factor. I am not going to be able to come up with the roots that this factor would give me through any means other than factoring it like this or using the quadratic formula. I could have come up with the -2 and the +3 with the rational zeros theorem, but I just can't for this. In order to find those roots, I'm going to have to take that factor and set it equal to 0 and solve. In this case, I don't have to use the quadratic formula on it. It's an irreducible quadratic, but I can solve it by subtracting 27 and then dividing by 3, which will get me a -9. Then when I take the square root of both sides, remember that when you take the square root of a negative number, that is I. So this is going to be I times the square root of 9, and we should have positive or negative anytime you take a square root. The square root of 9 is 3, so what I've got here is plus or minus 3i. These roots, these complex roots, are not things that you would have easily turned up using a rational zeros theorem. You could have tried to factor it, but in 1050 you are more likely to want to use your ninja algebra, like I said, of factoring by grouping, or one of the skills that you've developed for handling polynomials. Altogether then, my three roots are -2 from this factor, a positive third from this one over here, and then plus 3i and minus 3i. Remember that complex roots come in pairs, so if you have a plus 3i, you always have a minus 3i. And again, back up at the beginning when I was looking at the positive or negative roots, this is why I said we have either 3 or 1, because it's possible that you have a pair of irrational or complex roots. So there are your 4 roots for this one. Let's look at another example in the next video.